The following content is supported by victoris.org.
Hi everyone, my name is Chen Hao, and today I'll be presenting to you the H3 Physics 2022 suggested answers created by me and my friends. So let's jump into question 1. With a rod that is tipping over and it is going to eventually fall to the ground. So the question asks us to show that the initial angular acceleration of the rod is given by this formula. How do we do it? So let's first consider the external forces at play. This is the free body diagram. One is a normal contact force at a point of contact. Another one is the gravitational force acting at the center of gravity. We are going to take the pivot about the point of contact. So the only force that causes a moment is going to be the gravitational force. So by using torque equals to moment of inertia times angular acceleration, we need to find what is the moment of inertia. The moment of inertia for a rod is 1/3 ml squared when taking one end of the rod as the pivot. The torque is given by the force times the perpendicular distance to the pivot. The perpendicular component of the gravitational force when projected onto the perpendicular is mg sine theta, and the distance from the pivot to the point from which the force acts on is L/2. Solving for alpha would then give us this. From this we can deduce that the value of K is 3/2. Some insights from this question is that whenever you have a force that has an unknown value, such as the normal contact force in this question, when it's not immediately obvious what the value of the force is, it would be convenient to take moments about point that which the force originates from. This would cause that force to have zero contribution to the moment about the point because the distance is zero, hence effectively eliminating the force from the force body diagram. Now moving on to question 1b, determine an expression for the angular velocity of the rod just before it hits the ground. Now one sees that because alpha is the second derivative of the angle theta, effectively, from the kinematics point of view, we need to solve this differential equation. However, it is very difficult to solve it, so that's where dynamics comes in. So we jump from the kinematics perspective to the dynamics perspective, and the dynamics perspective makes use of conservation of energy. The initial kinetic energy of the system is zero, but because the rod has not touched the ground, there is some positive GPE. In contrast with the final scenario where the rod is laying on the ground, the rod would have some positive kinetic energy, but the gravitational potential energy would be zero. This allows us to obtain the relation that the gain in the rotational kinetic energy from the initial to the final is equals to the loss in the gravitational potential energy from the initial state to the final state. The expression for kinetic energy is half I omega squared, and the expression for GPE is mgh. Substituting in the value for I and solving for omega gives us the following expression. I'll leave it to you to do dimensional analysis to do a sanity check that the units make sense.